All right, we're live here at the Triangle Bitcoin and Business Meetup. We've got an interesting talk today from Sam Falah, and he is a senior software engineer at JP Morgan. He's going to be telling us about their take on Ethereum, basically an enterprise version of the Ethereum protocol that I expect is meant to offer, additional capabilities and performance over Ethereum itself. I have a little bit of experience with Ethereum engineering a wallet solution over the past year, and ran into a lot of interesting issues there that were quite troubling. So I'm very interested to see what Sam has to tell us about, how they're improving the Ethereum protocol, making it easier to use. So I'll just go ahead and hand it over to you.
Hey, thank you, Jameson, and thank you everyone else for having me. Very nice to be here to present to you Quorum and to hear a bit more about some of the issues that Jameson has faced with Ethereum and everyone else's questions. So we'll start with an overview of Quorum and why we decided to build it. So one of the key goals of this project was to look at one of the existing blockchain implementations that can actually work for us. First, can everyone hear me okay? Hey, Jameson, can you guys hear me?
Yeah, we are good to go.
Oh, perfect. Okay, so for why we did this and what were the project goals that we were looking for. First, we were starting off by building some POCs, prototypes on top of Bitcoin and top of Ethereum, and we felt very comfortable with smart contracts and where they would take us in terms of building our applications and getting the value from all of the participants on the network, reaching the consensus on a state for a smart contract execution or code execution in general. But for us, Ethereum was missing some key requirements for us to be able to use it inside of the company. So we were trying to play around with the public Ethereum client, most of the Geth client. We had to do a lot of tweaks on how do you improve proof of work. For us, the network is much smaller. That's when we started experimenting. The second thing that we look for is privacy, correct? So public Ethereum blockchain client has all of the transaction details available for everyone else to see, or all of the network to be able to view. And importantly, we were looking for governance in terms of who are the participants on the network. So pseudo-anonymous addresses do not work very well for us. We want to be able to tell who's sending the transaction and who are the participants on the network. With that, we created our permission fork of Ethereum. So we have added governance to it to be able to identify the participants, confidentiality, so to be able to hide some of the transaction details or the payload. We'll see how we do that a bit later on. And then security. So security comes by default by the features that are provided by the Ethereum client or by the Ethereum blockchain and blockchain in general through signing transactions and achieving consensus between all of the participants on the network. Now, with that in mind, with all of these features, we wanted to also stay as close as possible to Ethereum. So that was the value add of us going with Ethereum. It was already running in production for over a year at the time. So there was significant value for us there to make sure that we can use tested software. In general, we wanted to also use open source software, but at the same time, we wanted to give back and contribute. That's why we made Quorum open source. And a lot of the features in terms of API tooling weren't available for Ethereum. And these are some of the tools that we wanted to build and make available for everyone else to be able to use it inside of enterprise environments. Now, what we did with Ethereum, so we took the base Ethereum layer, we added permissioning to it. So by default, an Ethereum client allows any node on the network to be connected or to connect. What we did there is we modified the client slightly to be able to verify the nodes that are requesting to either send transactions or to connect to the peer or connect to my local node. with the initial implementation we went with, we created a static file you put on your local node or your local file system, and from there the client checks when it receives a connection request whether you had permission this client to connect to your node or not. Privacy, we added two new enhancements here. So we added a way for us to be able to communicate the actual transaction details or the payload through a peer-to-peer messaging layer. That's what we refer to as our Constellation client. And we started working with the Zcash team on adding their ZSL service to be able to transfer tokens from one party to another without having to reveal the original identity of the buyer or seller. And we'll talk about that a bit later more. By default, performance due to proof of work and due to the block size limit with Ethereum, or the default block size limit, it's in Ethereum, it's dynamic, but regardless, it was still too small for us to be able to put enough transactions in time to reach the performance requirements we want. So that was a slight tweak for us. We didn't have to make any significant updates, except for the consensus part where proof of work was a limiting factor for us. So we added a few other consensus algorithms. We started with something called Quorum chain. That was our initial implementation. It was based on smart contracts. So you would have a smart contract, you have the concept of a voter and block maker, and a new block gets created once the smart contract receives enough votes from the entire network that they have received and agreed with the block. Now that was mostly a proof of concept for us of how we can use smart contracts in a consensus algorithm. But we also wanted a formally proven consensus algorithm, so we decided to go with Raft for that. Raft gave us a lot of the performance benefits that you would get from a leader-based consensus algorithm, but did not have Byzantine fault tolerant added to it. So this is when we worked with the Istanbul team with IMEA. You'll see their name later on. They're part of EEA, and they had worked for almost a year. They proposed it actually for public Ethereum to be integrated in the main client there. But we like the fact that they actually had thought about signature verification, leader rotation, some of the features that allow it to have Byzantine fault tolerance. And one of the core features that we want in our type of environment is that you want settlement finality. That means after a transaction takes place in a company like ours, you cannot go back and say there was a reorg or there was a fork in the chain and you have to wait for settlement finality after a few blocks. Now the changes, or how does our Quorum client look like? So on the top, you'll see that we have, from an architecture standpoint, we have the dApp, which is the application on the top level. We have already existing applications, so we exposed those through APIs. So we did the integration through APIs. Then in the dApp, you have the smart contract. The smart contracts should actually be showing that they're running on the Quorum node, so everyone is running the smart contracts. Then we took the Ethereum code base for the Geth client, and we modified it slightly. That's how we created our Quorum client, or the Quorum node, as you see on the left side. Under Constellation, that's what we refer to as our peer-to-peer messaging layer or service. And what it does, it allows the nodes on the network. So if you look on this image on the right-hand side, we could think of the top as the Quorum nodes. They have the whole blockchain, and the lower section here are the Constellation nodes. And those have peer-to-peer connectivity. So when a transaction comes through, if you're familiar with Ethereum, everyone gets a copy of the transaction. Now, in our scenario, we have modified the transaction slightly to be able to provide a key or an address for the Constellation node that should receive a copy of the actual transaction. From there, when a transaction is sent to the local node, it checks with your Constellation node who are the other participants of this transaction. It would communicate the payload to them directly, receive a confirmation, And from there, it would take the hash of the encrypted payload and put that on chain. So all of the nodes on the network will see only hash of the encrypted payload, and only the participants will have the actual payload on their off-chain or local storage inside the Constellation service. And from there, once the actual transaction hits all of the other nodes on the network, they will check against their Constellation service to say, do I have any details on this hash? And if it does, if it has the payload, it will retrieve it, execute it through the EVM, and update its local state. If it doesn't, then it would just skip it would skip the transaction and move on to all the other transactions and block and go through the same process. Now, we've been working with many companies on this. These are some of the companies that are actually building on top of Quorum. So you have Accenture. Of course, Microsoft has templates on their Azure environment to simplify the deployment. EMEA is the company that did Istanbul for us. PLK.io did the Web3J implementation. And we have many other companies. We work directly with the Zcash team to do the integration for their ZSL layer. Now, in terms of ZSL, I saw that Zuko had presented to you recently, so you probably have some background on Zcash and how it works and zero-knowledge proofs. But what we were mostly interested in is the ZSL layer. And the reason that was very interesting for us is because once you have a token created on the network and it gets transferred, you have no way to be able to transfer it to a third party without disclosing the original sender or the original creator or who you bought it from. And given that one of the main features we were looking for is privacy, we wanted to avoid that. So we started looking at different implementations, and zero-knowledge proof actually, even though it was in early stages, we were very comfortable experimenting with it and trying to see how it would work for us. And from that, we worked with the Zcash team on their ZSL layer. Now, in general, we know what ZK snarks or zero-knowledge proofs provide, mostly being able to verify execution or computation without getting all of the details or having execute the computation. At the same time, they were working with a lot of the Ethereum developers, so they were working with the Parity team, so there was some experience with Ethereum in general and the Ethereum clients. So from there was just an easy relationship for us to experiment with them with the zero-knowledge proof and ZSL. So what ZSL provided us here is the ability to be able to transfer ownership of a token to a third party without exposing or revealing the original sender or the creator of the token. At the same time, of course, we can verify that the token that I'm receiving or the state update that is being requested from my contract can actually be verified. At this point, our proof of concept is limited to tokens or being able to verify tokens, but we're looking in the future to be able to verify also a state of smart contract through zero-knowledge proof. Now, so we have two privacy implementation on top of Quorum. We have Constellation. Constellation is our transaction manager, decides who on the network should receive a copy of the payload or the transaction details, given that you or only certain nodes on the network receive a copy of the payload. That means they can execute the bytecode of a smart contract or update the state of a smart contract. In terms of encryption, the question was always, why not just encrypt the data and put it on chain? For us, in terms of finance and regional regulation, they don't allow you to even put the encrypted data on chain. You want something where you can prove ownership of the data without actually putting any details of the data, even the encrypted data on chain. And that's why we went with only having a hash of the encrypted payload on chain for all of the participants to see, and that was acceptable. In this scenario, so of course you are the only node, so the private contracts are stored locally, which means only your node has a private state that has the smart contract, given that you're the only node and the other parties of the smart contract only receive the payload. That means they can execute it, update their local state. So for Constellation, one of the main updates we had to do to the Quorum client or to the Geth client when we forked it was to create the concept of a private state and a public state. And this is what we refer to as our, privacy engine inside of Quorum. So now the state is separated. There's a public state where everyone sees it and everyone agrees on it, but there's a private state where only the participants of the transactions for a certain smart contract will see that state. Now on the right-hand side, of course, in terms of zero-knowledge security layer, that gave us the extra benefit where when you don't share the actual payload and the complete details of a smart contract, you cannot provide any guarantees of ownership of an asset that was transferred or acquired by your node. And in this scenario, this is what ZSL gave us. So ZSL gave us the ability to provide a proof to any other third party that I want to resell a token to without having to reveal my original sender or creator, or who was the actual owner, original owner of the token. This is open source, so we'd like everyone else to join us and start contributing. Please visit our website. This is on GitHub, and of course we have a Slack channel. Please visit it to ask any questions. I can't take any questions now. I have a short demo, depending on how well we can share or how much time we have left. I can go through that too. So Jameson, it's up to you. Do you want to go through some questions or just do a quick demo, just showing a transaction and a smart contract and some privacy?
Yeah, I think we should be able to do some questions. I've got my first question was mainly around the public-private state, and then you had one little blurb where you said that the double spending reliance is dependent upon your application architecture. So is that essentially saying that you should only really be using the private state for data that is not relevant to the ecosystem or the system as a whole with regard to like the ownership of specific objects? Is it like you would only want to be using this private state for other attributes other than ownership? Or once you start pushing the ownership into the private state, is that when double spending is no longer something that can be guaranteed by the system?
It cannot be verified, correct? So it can, the original ownership can always be guaranteed in terms of transfer from the original owner, or it was created directly by you or issued by you. That's easily confirmed or verified. But once you want to resell that, you have to provide that you actually own it and you bought it from a certain other party on the network. And given that privacy is a core feature for us, we don't want to reveal that. So this is where the ZSL layer comes in.
And in terms of performance, I guess, what type of throughput are you looking to achieve? What type of machines are you looking for these different types of nodes to run on?
Yeah, so normally we have our internal infrastructure. It really varies, and throughput is a very open question. It always depends on the type of smart contracts that you're running, correct? So if you have just a pure transaction value transfer, if you're familiar with how Ethereum transactions look, if you're just doing some sort of value transfer, those can be in the hundreds, whereas if you start looking at EVM, very complex code, it goes to below 100. And we're talking here about the network being able to verify. There's some optimizations we can put there. Of course, the type of hardware that you're running makes a big difference, but it really varies depending on the hardware and the use case that you're looking at.
And have you stuck with the same? I'm assuming you're using the same virtual machine. Are you using the same languages like Solidity, or are you even supporting Serpent or any of those other ones?
So of course we're stuck. We stuck to the same EVM, so we support all of the languages that are currently supported, but mostly Solidity. So most of our work and our smart contracts are currently running on Solidity.
Any other questions? All right, maybe I'm the only one who had any questions. All right, let's, I guess, go ahead with the demo, and if other folks have questions at the end, we can always hit them then.
So I'm just going to share my screen again. Just bear with me for a second. Just let me know if you see my screen.
Yeah, we see a terminal.
Okay, perfect. So
if you can make the terminal like font size any larger, that would probably be helpful, since we're only seeing a few pixels. Yeah, no, that's pretty good.
Okay, perfect. So here, I did a cat on the script that I'm going to be loading in a bit. This is, if you're familiar with Ethereum transaction, this is just identifying the account. This gives you the API, the bytecode of the smart contract, and then instance of the smart contract being deployed. So what I'm going to do now, I'm going to attach to the Quorum node. So, what I want to show is I want to show privacy, correct? So I'm going to connect to one of the, I have 7 nodes running on the network. We can see that here. We can see 7 nodes here. These are 7 GET or Quorum nodes running. They're running Raft consensus algorithm. I'm going to attach to one of the nodes here, node 1. What I'm going to do, I'm going to load that script. And that script will basically send the transaction to create a smart contract between node 1 and node 7 on the network. So in this case, when I go to read the state, I should be only able to read the state of that smart contract on node 1 and node 7. Here we see the smart contract address, so I'm just going to copy that to record it when I look at the other node. And here we have the actual smart contract. So if I look at simple here, it's going to show me the API, and show me the contract address, and the simple methods I have on it. So if I do simple.get, here is going to show me the state of the smart contract. Now I'm going to do the same thing on a different node that we sent the transaction to. So if we look at script 1 here again, we're going to see this private for field, and here we have the address of node 7, which means only node 7 will actually get the payload of the smart contract here, and of course the sending node. If I connect to node 7, I should be able to get an instance for this smart contract. And see the same value, right? So this is just in the API of the smart contract here, and getting an instance for the smart contract. Now, if I try to do the same thing on any other network or any other node in the network, we won't have received the actual payload of the smart contract or the bytecode of the smart contract. That means we wouldn't have it in its private state. So if I try to do private here, it would just give us here. That means it does not have the code of the smart contract. And we can verify that by running this, just to be able to get details on the smart contract. We see the 0x, which is basically nil in this case. We can run the same exact command on the other nodes. So what this showed me is node 1 and node 7 do actually see the state of the private smart contract. Node 2 does not. And we verify that by trying to obtain the code from the private state, and it does not have it because its constellation node never received a copy of that payload. Now, if I do the same thing on node 7, if I run get code, I should be able to see the bytecode that I deployed. So that's it for the demo. If there are any questions.
Gotcha. And when you're defining, I guess, the visibility and the contract, that's a public key that is being used by the specific node?
Correct. So every node in the network will have its public key associated with its constellation node. And that's how we determine who should receive a copy of the payload when it's being deployed.
And of course, you are running it all locally, but you said, you've got these other consensus algorithms. I guess, do you still have this concept of block times, or is your consensus, basically instantaneous?
It's almost real time. So with Draft, you know how, if you're familiar with Draft, it's leader based. You have the followers on the network. Once they receive the transaction and confirm that they have received it, Raft will progress the actual blockchain. So in there, we have probably 25 to 50 milliseconds per block for the transactions.
Cool. I think we have a question here.
I just want to ask a follow-up on your question. So the encryption, is that for the smart contract and stuff, is it the public key of the receiving node that is used to encrypt the smart contract, the data part of the smart contract?
Yeah, so I'll answer that, but of course you can get all of the details of step-by-step how the encryption is happening. But in this case, we use asymmetric and symmetric encryption. So between the constellation node, just to be able to share an actual key for everyone to be able to decrypt it, we encrypt symmetric key using the public address of the other nodes. So every node, we take their public address and we encrypt the symmetric key using their public address. And from there, once they receive it, they can decrypt the payload.
All right, just a second here.
So in this example, are you using proof of work, or what's your consensus algorithm?
So we're using Raft. If I'm not sure, I don't think, am I still sharing the screen? Do you see it? No, 1 second. So,
Yeah, what you said it's the Raft consensus?
we're using Raft. So you can see here, if I do, well, I list the nodes that are running, you could see that it's starting in Raft mode. And for us, it's a pluggable consensus as long as you keep the network that you're running on the same consensus algorithm. So it's an option here that you provide. And of course, if you're familiar with Ethereum or in general how you would actually run it, you can't specify any consensus algorithm. But here we give you the options through parameters to be able to select the type of consensus algorithm you want to bootstrap your cluster with.
So I guess you said blocks are coming in basically on a matter of milliseconds. Does that mean you're still like creating and storing these tiny blocks, or is it only if there's a transaction?
Yeah, it's on the net, only when it sees transactions on the network, and it depends on how fast you're sending those transactions.
Gotcha. One more.
Sure.
So what's your transaction per second limit, if any? I'm sure there is some, right?
Yeah, there is limit, but of course it really depends. That's why I was telling Jason earlier. It really depends on the use case and the type of smart contract that you're running, and the cluster size, and the consensus algorithm that you're running.
Hi, so I heard you said the block time is around 15 milliseconds. Is that correct?
So it's around more like 50 milliseconds, depending on how fast transactions are coming in. And given that this is leader-based, it varies for the entire network based on the location of the other nodes or where are they located usually.
So how do you deal with stale blocks when two blocks are found at the same time?
So if you're familiar with the Raft, it's leader-based, correct? So there's no two blocks. This is not proof of work where two different nodes can create a block at the same time, but there's only a leader elected when you bootstrap the network, and based on that, unless there's failure, that leader will manage creating the blocks for the network.
Yeah, I guess. Well, when these nodes that are on the network that are actually performing the consensus, are they permissioned in some way? Like, do they have special rights to be a part of the consensus, or is it just anyone who wants to join the network?
No. So one of the main updates we had to do on the Geth client when we forked it is allow certain nodes to be able to connect only. And when you configure your Raft cluster, you specify the nodes that are going to be participating in the Raft consensus algorithm.
Yeah. So you can get a very different performance, trade-off when you have different security models like that. So higher performance, definitely a lot easier when you're able to control the actors who are in the system, right?
When you can control the actors, the size of the cluster, when you don't have to worry about who will actually create the block for you. So you have leader-based consensus algorithms, and those, of course, by default, give you much faster throughput than you would expect with proof of work.
All right. I think everybody's happy. So now we just need to get anybody who wants to learn more about it. Like you said, it's all open source. You can check it out, I guess, both on the JP Morgan site and is the project on GitHub or some other repo?
On the JP Morgan Chase, so GitHub repository, there you'll see Quorum Constellation and the example source code that I downloaded for you today.
And would you say, I guess in general, because the actual language is the exact same, with the primary difference being you have that ZSL functionality, anyone who has an Ethereum smart contract should be able to just take it and run it on one of these Quorum networks, right?
Yes, absolutely. They should be able to spin up nodes and be able to run the same smart contracts that they've created for public Ethereum.
Cool. Sounds good. Well, we really thank you for your time, Sam, and it's been great having you and learning more about Quorum.
Great. Thank you very much, guys. Thank you. And feel free to reach out with any questions or through GitHub or Slack.
Thanks.
Thank you. Bye-bye.
Good night.